All right, so here's the problem. Detecting prime numbers with functions. So implement a function that takes an integer value and returns true if the integer is a prime number and false otherwise. The function should have the following signature. So this is what the function looks like. The name is prime, and it takes an integer n and returns true or false. That means it returns a Boolean value. That's the data type. Use an assert statement inside the function to check the precondition that n is greater than 1. So I guess it's meaningless to ask the question of whether an integer equal to 1 or less than 1 is prime. So that would be not part of the definition of prime number. So it would be a meaningless question, I believe. So when the function is called, n should be 2 or larger. So we just use an assert statement in there just to check that. Include the function in a console program that calls the isPrime function with a range of values that tests several common cases as well as the boundary cases. Use an assert statement for each test case. For example, the following tests that the function returns false for the value 100. So 100 is not prime. So if we pass 100 to the isPrime function, the function should return false. It's not prime. So we put that inside of an assert statement. This expression right here, this is where we're invoking the function. We invoke a function. You can think of it as a function being replaced by its return value. So this will be replaced by the Boolean value false, assuming that we implement isPrime correctly. And so we compare false on the left-hand side with false on the right-hand side. So that comparison is true. That's a truthful, that comparison is true as opposed to false. So when you pass true to assert just does nothing. Just lets the next statement execute. But if isPrime was implemented incorrectly, isPrime would return true for 100. And then true would not be equal to false, and the assert statement would then terminate the program with an error message. So this is a form of one way to do automated testing. And in real automated testing, in industry, you don't use assert statements. You use test cases, and there are frameworks that developers use to do test cases. But the assert function is important to learn about, so that's why I'm using it for this purpose. There's a header for this CAssert. You need to include that in the program to use the assert function. All right, so once again, we need to implement this function, isPrime, and test it with assertions. So if we're going to call this function, it needs to be known before we use it. So if we define it here, we'll define it with a stub. We'll just return true always. That's called a stub. We didn't fully implement the function yet. Yeah.
What's bool?
Bool is a data type like int or double or string. It's a type of data. But the data values there's only two data values, true and false. So it's a variable. If you declare a variable to be of type bool, you can only store true in the variable or false in the variable. The variable doesn't store a number, for instance. I mean, actually it does internally, it's a number. All right, so that's how you declare a function or define a function. Once again, we're just implementing it first as a stub. It's not the full implementation yet. We just want to get the test code written first. And then here's the main function, and then we'll do some tests, and then we'll print all tests passed. So if an assert statement fails, we won't test all tests passed. We'll we won't print all tests pass. We'll print an error message. Let's just see how this builds and runs. All tests pass. So some tests. Well, let's do the test that's shown, that was used as an example in the instructions. We'll assert that calling is prime with 100 returns true. Oh, sorry, false, right? 100 is not prime, so that should return false. Now, we've implemented the function as a stub, so we're going to have a failed assertion. And that's what we intend to do at this point in the development. We intend, predict that the assertion will fail. Up. What's the problem? Assert was not declared in the scope. We need to, there's a header file for that defines assert. It's called cassert. Assert was not declared in this scope. Right? So now it is declared in this scope. And it works. So what's going to happen when we run it? It's going to say all tests passed? No. We're going to get a failure in line 11. There it is. There's the 11 right there, line 11. Assertion is prime 100 equals false, failed. And then it says aborted. So it terminates the program right there. Doesn't print, doesn't get to line 13. And we'll need, before we implement the function, let's go ahead and create some more test cases. The other problem, I asked for 8 test cases. Let's go ahead and use 8 test cases. So it's important when you do testing to test boundary cases. So 2 is the smallest prime number. So let's try 2. Oh, by the way, that should be true. And 3 is, close to 2, so that's not exactly boundary case, but almost. And then 4 is the first non-prime number. So that should be false. And 5 is the first prime number after the first non-prime number. And then we just keep going here. 27 is an important case to test, I have discovered. That's false. Right? That's 3 cubed. And some other ones, 100 and 101. Is that prime? So I don't even know, right? I don't think 101 is divisible by anything. Let's leave it like this. Let's make this 105 is not prime, 100 is not prime, and 42. Some people like that number. And there we go. Maybe we need a large prime number in there. Like 29, I believe that's prime, right? That should be true. That's prime. All right, so just check that it builds. Of course, it's going to fail. And that's what we expected. It passes on these 2 because, well, we're returning true, but it fails there. So now it's just a matter of implementing the function is prime. And to check to see if a number is prime, the algorithm that we're using is that we're just going to try to divide n by 2, then by 3, then by 4, and so on. If we find that any of those numbers evenly divides into n, then we know in that moment, when we discover that number, that n is not prime. But if we try all the numbers, and none of them divide evenly into n, then we can conclude that n is prime. We'll use a loop for that. We'll start at 2. That's where we start from. We'll divide by 2, then we'll divide by 3, and so on. And this I needs to be less than n itself, because we don't want to divide n by n. That will always work, right? And then increment I. And we check if n mod I is 0. So n mod I, that means divide n by I and get the remainder. What's the remainder after dividing n by I? Well, if the remainder is 0, it means that I evenly divides n. In that case, we're going to return false. We know on the spot right there in that moment that n cannot be prime because we found a divisor I. So we're going to return from the function false. Now this breaks out of the loop. This return statement, we leave the function, we return back to, say here, for instance. So we'll branch back to here. So when we call is prime here with 4, when we call is prime with 4, then 4 will come in through n here. And then we're going to enter into this loop. We'll start with I equal 2. We're going to go 4 mod 2. 4 mod 2 is 0. So then we return false. That means this function here evaluates to false. And then once the system evaluates that call to false, it has the value of the left-hand side of this comparison. And it compares it, of course, to the right-hand side. We've got false equals false. That's a true statement. False does equal false. And so the assertion doesn't do anything, just quietly term finishes. And then the next statement in line 17 runs. Now, if we finish this loop and we never return false, it means we never find a value I that evenly divides into n. No value divides into n. So n will be something like 7. Right? And you're trying to divide it by 2, 3, 4, 5, and 6. None of those numbers divides into 7 evenly. And so when you exit the loop, you know that you didn't find a divisor, so you can return true. N is prime. So we're going to test this with this automated test code. So we're not going to do visual inspection. Well, we will. We just wanted to see it say all tests passed. That's the only visual inspection we need to do to determine that the function is written correctly. So we have, in that sense, we have automated test code. All tests passed. There it is. Now, if we had done this wrong, like if we had started from, if we had done something like this, if n mod 2 is 0, okay? I've seen that before. That just means it's even. That means if n mod 2 is 0, that means that n is evenly divisible by 2. That means it's even. Well, what about something like 27? 27 is not divisible by 2, but it's divisible by 3. So 27 is not prime. So this will give us a false solution. And let's watch the test code catch that. And we want good test code. See, is prime 27 equals false, that assertion failed. It was because we haven't correctly implemented this function.